So in this video, I'd like to talk a little bit about trig identities, and we're going to look at some examples of where we might use them to prove some other more complicated identities. So to start with, the trig identity you should definitely be familiar with is what's called the Pythagorean identity, which says that the sine squared of something plus the cosine squared of something is equal to 1. And remember that the angle you're using for both sine and cosine has got to be the same. So the sine squared of 45 degrees plus the cosine squared of 45 degrees is equal to 1, because the angles used were the same. Whereas if I said something like the sine squared of 10 degrees plus the cosine squared of 60 degrees, that's not 1, because the angles I used were different. And the same is true for pretty much any trig identity. Now there are two more important double angle identities which you should learn. Now some people say you should learn how to prove or derive these, and I agree that you should, but I also think that you should just learn them off by heart. I mean, these come up so often in maths, and you're just going to save yourself a lot of pain later. Just trust me on that one. So the first identity says that the sine of 2x is equal to 2 times the sine x times cosine of x. And the second identity says that cos of 2x is equal to cos squared x minus sine squared x. Equivalently, that's exactly the same thing as 2 times the cosine squared of x minus 1, or 1 minus 2 sine squared of x. How are these all related? Well, if you use this identity and plug that into this one, you can get these two identities here. But again, I highly recommend that you just memorize these, because you'll save yourself a lot of trouble. So let's try some examples. Let's look at the tangent of 2x equals 2 times the tangent of x over 1 minus tan squared of x. So this is the thing we want to prove. So I'm going to start from the left hand side, and I'll ask you to recall that the tangent of x is equal to sine of x all divided by the cosine of x. Now this is true as long as the angle I'm using is the same. So it's perfectly reasonable to then say that the tangent of 2x, so just replacing x with 2x, is equal to sine of 2x divided by the cosine of 2x. And the same is true for 3x. I could say tangent of 3x is equal to sine of 3x over cosine of 3x. It's still valid because the angle I'm using is the same. So bearing this in mind, let's now use this to prove this identity. Well, the tangent of 2x is equal to sine of 2x over the cosine of 2x. Using my double angle identity above, I know that sine of 2x is this thing. So it's equal to 2 times the sine of x times the cosine of x. So if I expand the top, that's 2 times the sine of x times the cosine of x. I've then got to divide that by the cosine of 2x. So let's look at the identities for the cosine of 2x. So I've got cos squared x minus 1, 2 cos squared x minus 1, and 1 minus 2 sine squared x. I'm actually going to use the top one, cos squared x minus sine squared x, and you'll see why. So cos 2x is the same as cosine squared x minus sine squared x. Okay, so looking at this thing we've got here, this expression, we want to make this look like this. So how do we do that? Well, we want tangent of x on the top. So at some point we're going to have to divide by a sine or a cosine. So let's try dividing by cos squared and see what happens. So I'm going to divide the top and the bottom by cos squared. So I'll put this in brackets. I'm going to take the top, so 2 sine x times the cosine of x, and I'm going to divide that by cos squared of x. So cos squared of x. Whatever I do to the top, I've also got to do to the bottom. So I've got the cosine squared of x minus the sine squared of x in parentheses, all divided by the cosine squared of x. Okay, so now how does this simplify? Well, I can rewrite the top as follows. I know that's the same thing if I just split this fraction up, which I can do because it's just multiplication. This is the same thing as 2 times the sine of x, if I put this in brackets, over the cosine of x, so that's dealing with one cosine, and I'm going to multiply that by the cosine of x over the cosine of x. So this is exactly the same thing as what I've done up here. I've just split this fraction up, because when I multiply these two things together, I get this back. So, 2 sine x cos x, all divided by cos x, which is cos squared x. So that's the numerator, and now I've got to divide by this thing on the bottom. And this thing on the bottom, well, I've got cos squared x minus sine squared x, so I can again split this up into fractions. So this is the same thing as the cosine squared of x over the cosine squared of x. Then I've got a minus sine squared of x, all divided by the cosine squared of x. Okay, well, this should look familiar to you. So this should look familiar to sine of x over the cosine of x. You know that that's equal to the tangent of x. So we've got 2 tangent of x, which looks very helpful because this is what we want on the top. We've also got cos x divided by cos x, but cos x divided by cos x is just 1, because anything divided by itself is 1. So this is just 1. So this is just 1. So that takes care of the numerator. Let's look at the denominator. Well, cos squared of x divided by cos squared x, by the same argument, that's just 1, because when I divide anything by itself, it's just 1. Minus sine squared x over cosine squared of x. Well, the sine of x divided by the cosine of x is tangent of x, and so the sine squared of x over the cosine squared of x, if I just square the whole fraction, I have to square the expression, so that's just a tan squared of x. So when I square this thing, I get this thing. So this is just the tan squared of x. And I believe I'm done now. Yes, I'm done, because I've got 2 tan x over 1 minus tan squared x. So basically what I did was divide by the cosine of x and use my double angle identities. So that's the first identity done. So let's look at the second one. So we've got to prove now that the sine of y plus the cosine of y all squared is equal to 1 plus the sine of 2y. Well, again, I'm going to start from the left hand side. So this is what I'm going to do. Let's expand this bracket. Well, the sine of y plus the cosine of y squared is the same thing as multiplying by itself. So this is sine of y plus the cosine of y. Okay, so now if I just expand the brackets, what do I get? Well, I've got the sine of y times the sine of y. So I've got to do this term times this term. What do I get? Well, I get sine squared y. Now if I do this term times this term, I get sine y cos y. Now if I do this term times this term, that's cos y times sine y, which is sine y cos y. So plus sine y cos y. And lastly, I've got cos y times cos y, which is just cos squared y. Cos squared y. Now I'm going to put the sine squared y and the cos squared y together. So I'll put the sine squared and the cosine squared together, and I'll get this. So I get sine squared y plus the cosine squared of y. Now I'm just rearranging the terms. Plus sine y cos y plus sine y cos y. Well, these are exactly the same terms, so I can group them together as 2 sine y cos y. Well, this is just the Pythagorean identity. Sine squared of anything plus the cosine squared of that same thing is just 1. Plus 2 sine y cos y. But I know that this is the double angle identity for sine of 2x, because if I go back to my identities, I've got sine 2x is equal to 2 sine x times the cosine of x. So I can use this here. So I can just rewrite this as 1 plus the sine of 2y. And that's the proof for this identity. Let's look at the final example. And that asks us to prove that the cosine of theta minus the sine of theta, all divided by the cosine of theta plus the sine of theta, that's equal to cos of 2 theta over 1 plus sine of 2 theta. So again, I'm going to start from the left-hand side. Now, it might look a little bit confusing at first, but I want this to look something like this. I want to see if I can extract a double angle from these single angles. And what do I mean by this? Well, I want to make this look like one of the identities above. So I know immediately that cos 2x is involved, so I want to try and get one of these identities involved somehow. So how am I going to do that? Well, you'll notice if I multiply this thing by cos theta plus sine theta, I know that by the difference of two squares, I'll get cos squared theta minus sine squared theta. So let's see if that helps. So if I multiply the top and the bottom by cos theta plus sine theta, what happens? So what happens when I do that? Well, I've got the cosine of theta minus the sine of theta, all divided by the cosine of theta plus the sine of theta, and I want to multiply the top and the bottom of this fraction by cos theta plus sine theta. So I'm going to multiply this by the cosine of theta plus the sine of theta. Cosine of theta plus the sine of theta. And what happens when I expand this? When I expand this, I just get the difference of two squares, right? Because I've got something minus something times something plus something. So a minus b times a plus b, or in this case, cos theta minus sine theta times cos theta plus sine theta. So this is just the cosine squared of theta minus the sine squared of theta. I've now got to divide that by the product of these two things. And when you take the product of these two things, this is what I get. I should get the cosine squared of theta plus sine theta times cos theta plus another sine theta times cos theta, and finally plus sine squared theta. So let me just make my divide sign longer. So now I've got cos squared of theta minus sine squared of theta in the numerator. And just as I showed you, this is equal to cosine of 2 theta. That was one of my double angle identities. So this is just equal to cosine of 2 theta. Now for the bottom, I know that cos squared of something plus the sine squared of something is 1. So that's just 1. And I've got these extra two terms which can be combined together because they're the same term. So 1 plus sine, or rather 1 plus 2 sine theta cos theta. Now again, I can use the double angle identity here because I know that 2 sine theta cos theta is the same thing as sine 2 theta. So this whole expression becomes the cosine of 2 theta all divided by 1 plus sine of 2 theta. And it appears that that's what I wanted to prove. So that's the proof of that identity.